Alright, in this lesson we will take a look at an introduction to graphing using calculus. And of course in algebra you learn how to graph a straight line. All you need is to plot 2 points. You learn how to graph typical functions like a quadratic, a U-shaped curve. You could maybe locate the vertex. But the moment you get beyond second degree, graphing using techniques of algebra become very tedious and not so convenient. So calculus will help us pinpoint some important characteristics of a function. For example, the maximums, the minimums, the inflection points, which we're going to learn about today. And then graphing the function will be easier. So let's first get some ideas about some terms that we're going to be using in this section. And then we will take a look at some examples. So for example, we're going to use the terminology concave up and concave down. So the question is, over which intervals is a given function concave up and over which intervals is it concave down? So let's take a look at the graph. So clearly over this region it's concave up, right? We usually give the regions over the x-axis. So that region would be like negative infinity to 0. This function is concave up. And where else is it concave up? Like from this point A roughly to the point B, it's concave up, right? So from A to B. And also from C and beyond, it's concave up. So C to infinity. So over these 3 intervals, this function is concave up. And where is this function concave down? So over this interval, it's concave down. So you would give the region in terms of the x values. So basically from 0 to A, it's concave down. And where else is it concave down? Also from B to C, right? So over the interval from B to C, this function is concave down. Now if I ask you, where did this function change its concavity? You could say at the point A, concavity changed. Basically right here, whatever the function f of x value is there. At the point where x equals b, concavity changed, and x equals c is another point where concavity changed. We call those points inflection points. So those are very important points along the graph, and calculus will help us locate them so that the graphing the function will be easier. But also note that over here, over 0, concavity changed. So first it was concave up, then after that 0 point it was concave down. So note that concavity also can change across a point of discontinuity. So it can change across inflection points. It can also change across a point of discontinuity. Here's a similar question. This time we want to indicate intervals where the function is increasing and where it is decreasing. And then a similar question, indicate where did the function change its direction from increasing to decreasing or vice versa. Let's first look for the increasing regions. So over this region the function is increasing, right? So increasing from 0 to A and also from B to C. That's about it, because when you go from left to right, the graph should be rising. Those are the intervals where the function is increasing. Over the remaining intervals, the function is decreasing. Like over here, you go from left to right, it's decreasing. Then over here, it's decreasing, and over the last interval is decreasing. So those intervals are negative infinity to 0. Again, we give them over the x-axis. From A to B, and also from C to infinity. The function is decreasing. Now, let's take a note about at which points or across which points the increasing, decreasing nature of the function changed. Well, it changed across the point x equals A, x equals B, x equals C. What kinds of points are these? If you say they're like maximums and minimums, you are correct. So these are called local or absolute extrema for the given graph. So it is important to locate those points first, as well as the inflection points as you're trying to graph a function, because they will tell you a lot about the graph. But also notice that it was decreasing up to here, and then it was increasing afterwards. So it changed the nature of its increasing, decreasing nature also across a point of discontinuity. And this point right here is a sharp point, so notice that it can change its nature across a sharp point. This point would be called a point where derivative is not defined. And the reason it's not defined is because, how do you define the tangent line there? Do you define it in this direction? Do you define it in that direction? So it becomes like this discontinuous in terms of the tangent line. So basically, it will be important to locate, when we graph a function, points of discontinuity, points where derivative does not exist, points like that, and also points where you have maximums and minimums, in other words, where slopes are horizontal. We call those critical points. So it will be important to locate those points, because those points hold the key to where this function will be increasing or decreasing. Now let's take a look at this function for a moment. And let me shade it a little bit so you don't have to look at everything at once. So we have y equals f of x, increases up to a, decreases afterwards. So we can clearly say this function is increasing from negative infinity to a, correct? Basically over this region. And over the x-axis from negative infinity to a, this function is increasing. And over the second interval from a to infinity, this function is decreasing. Now what can we say about the derivatives? So up to a, look at the slope of the tangent line. All of these lines have positive slopes, right? And the slopes are actually going towards zero, but the point I'm trying to make here is that when a function is rising, the tangent lines are always going to have positive slope. So that means that your derivative will be positive. And the same goes that way. If the derivative is positive, one can say that the function is increasing. Similarly, when the function is decreasing, take a look at the slopes of the tangent lines. They're all going to be negative slopes. So the derivative, which represents the slope of the tangent line, right, it will be negative. And the same can be said backwards. So when the first derivative is negative, the function will be decreasing. So in a few moments, I'm going to review those, because these ideas are going to help us put together a plan of action when it comes to graphing polynomials and other sorts of functions. Now, about concavity. The first one we see here, this graph, is it concave up or concave down? It's concave up, right? As you go from left to right, it's bending upwards. That's concave up. And also for a concave up function, basically tangent lines lie below the function. Now, what can you tell me about the slope of the tangent lines in a concave up graph? Now, this is also concave up, right? So it's not always has to be positive slope or negative slope. It can vary. It doesn't always have to be positive. It doesn't always have to be negative. But I want to point out to you here that slopes are getting steeper in a concave up graph. Like here, maybe the slope is 0.5. Maybe here the slope is like 1. Maybe here the slope of the tangent line is 2. So the slopes are increasing. So the function is, in this particular case, not only is increasing, but the rate of increase is increasing as well. So because slope was first 0.5, then 1, then 2. So that's the characteristic of a concave up function. So it's concave up, slopes are increasing. And remember, slopes is another word for that is f prime. So that means f prime is increasing. And here's the tricky part. This is a little bit hard to follow the following argument, but pay really close attention if you can. If something is increasing, let's review what we did earlier. Something is increasing, like here, f was increasing. Then what happened to its derivative? Its derivative was positive, right? Well, in this situation, the slopes are increasing. F prime is increasing. So if a quantity is increasing, then its derivative, so F prime prime, should be greater than 0, based on what we learned up there. So F prime prime happens to be F double prime. So here's the conclusion. If a graph is concave up, we expect the second derivative to be positive. And you can do a similar argument with concave down, and you're going to see that if something is concave down, slopes are decreasing. That means F prime is decreasing, and a quantity decreasing means its derivative is less than 0. So F double prime is less than 0. So now let me show you how we can put all of these ideas that we've discussed together into a plan of action, and you should have this handout in your on the website. Okay, so let's take a look. Okay, so here's going to be the steps that we follow to graph a function. First, we're going to want to find the relative max and min. That will also help us to find intervals of increase and decrease. To locate the relative maximums and minimums, we're going to find all points where the derivative is 0. Remember, those are the points where you could have maximums and minimums, soft peaks or valleys. Also, we need to find where f prime is undefined. Those are the points where you could have sharp corners. These points are called critical points. They're also candidates to be relative max or min. Then we will place the critical points on the number line, and we will select test values from each of the intervals determined. And we'll determine the sign of f prime. So we're going to say that this point was a critical point, this point was a critical point. So we're going to try to find, is f prime positive, is f prime negative over these intervals. I'll show you a way to do that. If f prime is negative, that means the graph is decreasing. Positive means the graph is rising. Negative means the graph is decreasing again. So already you would have a lot of information. Like here, you have a minimum because it's decreasing and then increasing. Here you would have a maximum because it's rising and then falling. So over here, again, it repeats the points from earlier discussion. That if f prime is positive, the graph should be rising. Negative, it should f prime negative, the graph should be falling. Also, let's take a look at the second derivative analysis, and then we'll do an example. Okay, to find inflection points and intervals of concave up and down, we will first look at the points where the second derivative is 0 and where second derivative is undefined. These are going to give us the candidates for inflection points. And remember, concavity changes across inflection points. And once again, we'll follow something very similar to the previous steps. We're going to put those points found on the number line, let's say 2 and 5. And let's say we have something positive. So we're going to check the sign of f double prime, because f double prime, second derivative of a function, tells you about concavity. If second derivative is negative, as it says down here, then you expect the function to be concave down. If second derivative is positive, you expect the function to be concave up, and so forth. So we're going to determine intervals of concavity based upon the second derivative. And to finish the graph, we may graph some of the y-coordinates of the important points found in steps 1 and 2. We're going to use the f prime chart and f double prime chart to get our directions, rising, falling, concavity kind of information, all going on the final graph. Okay, let's take a look at an example. So let's take a look at this example. F of x equals x to the 4 plus 2x cubed. So it's a polynomial of fourth degree. Again, techniques of algebra might have been very restricted to graph this function. We're going to graph it and indicate all important points, including maximums, minimums, inflection points, and also we want to indicate the intervals of concave up, down, increasing, and decreasing. So everything we can possibly tell about this function, that's what we want to do here. So following the steps we just looked at, step number 1, we're going to get information about max, min, and increasing and decreasing nature of the graph. So first we're going to find the first derivative, and we will set that equal to 0 because we're looking for points where slope is equal to 0. So the first derivative is 4x cubed plus 6x squared. Setting that equal to 0, let's solve for x. I will factor out a 2x. As a matter of fact, it looks like I can factor out a 2x squared instead of factoring it in 2 steps. Let's just go in one shot. Take out a 2x squared, and that will leave us with 2x plus 3. And if you like, just multiply it back, check to see that indeed you are getting the original function after the factorization. So if the product of these quantities is equal to 0, either 2x squared is equal to 0, or 2x plus 3 is equal to 0. If you solve each one individually, you will have that either x is equal to 0, because you divide by 2, then you take a square root of 0, you still get 0, or over here x equals negative 3/2. So these are called the critical points, and you may also say, are there any points of discontinuity of f prime? Well, f prime is just a polynomial within itself. It's continuous everywhere, so the only source for critical points here are points where f prime is equal to 0. These 2 points we just got, let's put them on a number line. Okay, so now we want to know the sign of f prime because that will tell us about the nature of increasing, decreasing properties of the function. So let's do a quick selection of test values and x versus f prime. And remember, f prime was in factored form 2x squared times 2x plus 3. Okay, so we need to pick some test values. I'm going to place the test values at the top so I'm not confused with them versus the critical points. So like over this interval, I might select -2. In the middle interval, I will select -1. So that basically any number between -3/2 and 0 would do, but I'm selecting the easiest possible option. And from 0 to infinity, I'm going to select the point 1. Let's plug these points into our f prime function. And why are we plugging them into f prime? Because remember, if we know if f prime is positive, that will tell us the graph is rising, right? Or if it's negative, that will tell us that the graph is falling. So that's good information to have. Now, we don't even want to know the numerical value. Like -2 squared is always going to be positive, times 2 is positive. And if you plug it in over here, you get 2 times -2 is -4 plus 3, that's -1. The end result is negative. Now substitute -1. Again, since it's 1 squared, this portion will be positive. The second portion will be positive as well. Plug in a 1 for x. First portion is positive and second portion is positive. So based on what we determined, we have f prime was negative in the first region, positive, and positive in the next 2 regions. So we already have a rough idea about this graph because this is a polynomial function. It's a continuous function, has no holes or jumps. It's going to be a smooth curve. And based on the f prime chart, if f prime is negative, the graph is decreasing, right? If f prime is positive, which it is for the rest of the region, the graph should be rising. So we have a very rough graph right now that it will be falling up to -3/2 and rising afterwards. What do we need to do next? What does our step number 2 tell us? Check out with your handout. Second derivative, right? So you do an f double prime of x, because now we're trying to get information about concavity. So take the first derivative and differentiate it one more time. And once again, set it equal to 0 to try to find potential inflection points. So this time I'm going to take out a 12x and solve for x. So we get 12x is 0. You can divide both sides by 12, and that means x is 0, or x is -1. So we'll do something similar to what we did earlier, but this time for f double prime. Place the important points on the chart from the smallest to the largest. As a matter of fact, I'm going to try to just line this up with the chart above. So -3/2 is over here. So I want to go up to -1. And 0 was over here. Okay, so we want f double prime. So now we need to do a sign chart for f double prime. And the test values this time, I'm going to select are -2, -1/2, and 1. Plug them into f double prime this time, which happens to be 12x times x plus 1. Again, if you plug in a negative for x, you get negative for the first portion, and you get negative for the second portion, so the end result is positive. If you like, you can use your tables option. Put your f double prime in y and then go to the tables and just plug in, -2 and so forth. That would be another way to get your results. At -0.5, 12 times -0.5 is negative. -0.5 plus 1 is positive. The end result is negative. At 1, we get positive times positive. The end result is positive. So it appears that up to -1, the function is positive. Rather, the second derivative is positive. Between the two roots, we have negative for second derivative, and then positive again. What does this tell me? It's concave up, right? If f double prime is positive. Let me show you that slide once again. Right here. If f double prime is positive, the function is concave up. So, and if it's negative, it's concave down, and over here, concave up again. Now we're ready to put the pieces together, and you could get the corresponding y coordinates. So the important points we got in the 2 steps above, let's put them on the on this chart. So we have -2, -1, and 1. Excuse me, those are my test values. What I want to put is, I want to put my important points that we got, which are this point, the points that you got as your zeros of your f prime and the zeros of your f double prime. So those are the ones I want to place on this number line. So this, we have -3/2, 0, and also we got here -1. So I'm going to put them on this chart from the lowest to the highest. And now we're going to plug them into f of x, the original function, because I want to know the heights along the graph. How high is the graph going to rise? So at -1.5, you can plug these the number in, and you're going to get -1.7. At -1, it's -1. At 0, it's 0. So I have everything I need now to finish this graph. And I will begin by plotting the points. So I have negative 1.5. So let's say this is negative 1. Let's say this is negative 2. And let's just say that this is negative 1. This is negative 2. So the first point, negative 1.5 comma negative 1.7. So roughly speaking, over here somewhere. Next one, negative 1 comma negative 1. Over here somewhere. And 0 comma 0. Now there could be a million different graphs going through these 3 points because this is not a line, remember, this is a curve. But our f prime chart and f double prime chart will guide us. First of all, you want it to be decreasing. You want it to be decreasing up to negative 1.5 and increasing afterwards. So let's do that on the chart. Decreasing up to negative 1.5. So I'm just going to put some dotted lines. This is a skeleton of the graph right now. Decreasing up to negative 1.5 and increasing afterwards. Remember, this point had an x-coordinate of negative 1.5. So from the f prime chart, you get the skeleton. But to mold it, to give it shape, you need to go to f double prime chart. So let's take a look at that one right now. Okay, f double prime chart is telling us the graph should be concave up to negative 1, then concave down to 0, and concave up again afterwards. So let's mold it. Concave up to negative 1, x equals negative 1. So the graph should be following the dotted line pattern, but molded to be concave up to negative 1. You got to follow the dotted line. That's your skeleton. That means the graph should be rising. But now it should also be concave down based on this. So it should be rising and concave down. Can you picture how that's going to look like? While at the same time going through those plotted points. And over the last region, concave up. So it should go in that direction that we have the dotted line. But this time, bending upwards, going concave up. Now at this point, you could actually graph this function on the calculator, the original function, x to the 4 plus 2x cubed, and you could verify that the graph is going to look like this. And sometimes the graphing calculator doesn't give you all the details, so you may have to zoom in specifically, like in this case, I would make this rectangle from negative 5 to 5 perhaps for the x, and maybe negative 3 to 5 for the y. Because if you make it like negative 10 to 10 in both directions, you may not see all the details. And on the exam, you can check something on the calculator, but usually, for the obvious reasons, I will need to see all the work. And typically, I don't ask you an entire question like this. Typically, I will ask you like, perhaps this could be the first part of the question. Just tell me where is it increasing and decreasing, and what are the relative maximums and minimums. Or I might say, okay, where is it concave up and down, and what are the inflection points? Or sometimes I might give you the chart for f prime and f double prime, and ask you to create for me a tentative graph, a rough draft for the graph. Now, let's list our important points here. For example, where is this function? Let's first write down relative maximums and minimums. You really don't need the entire graph to get that information. You could go to your f prime chart. You see this graph? It was decreasing up to negative 3/2 and increasing afterwards. You can see right there that the minimum is going to be at negative 3/2. So that is our answer. And is there going to be an absolute maximum or relative maximum? In this case, no. There is no like top of the hill kind of situation. So we just have a relative minimum here at x equals negative 1.5. And we got the y coordinate there was negative 1.7. And sometimes I'll even accept just an x coordinate. X equals negative 3/2. No relative maximum in this case. And what about inflection points? where did concavity change? Again, you don't need this last graph to get the information. You can just come over here, and where did the sign change from being positive to being negative? At -1, right? And also at 0. And you can see on the graph, at -1, x equals -1, x equals 0, the concavity changed across those points. So the inflection points are x equals -1 and x equals 0. Or alternatively, we could say -1, 1, as well as 0, 0, because we already got the y coordinates for those points. But when there will be times where you will not know f of x, because all I will give you is f prime, because I don't want you to do it on the calculator. I want you to do it just from using methods of calculus. So I may give you f prime. In that case, the only thing you won't be able to do is this chart here. So you will not be able to get heights, but that's okay. You can still get, you could have done a situation like this. You could have said, okay, my graph looks something like this. You won't know what the heights are, but you can still label the points. Like the minimum, you can say this is like x equals -1.5. Let's say changes concavity at this point, x equals -1, and so forth. So you can still give me a rough graph even without the y coordinates. Where is this function increasing? Basically everywhere after this point, right? So from -1.5 to infinity, the graph is rising. In this region here, it looks like maybe it's not rising. However, it's still rising. It's just concave down, but it's still going up, 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 up. But the rates are not increasing. And sometimes it's easier to go to the f prime chart. When is this function rising? Where f prime is positive. And that happens to be from -3/2 to infinity. So because after the point -3/2, this graph is increasing. We have positive derivatives. So -3/2 to infinity, the graph is rising. When is it falling? From -infinity to -3/2. When is it concave up? -infinity to -1. And also I put a union or semicolon, either one is okay. Union from 0 to infinity is concave up. And of course it's concave down everywhere else, which is between over the interval from -1 to 0. So you've listed everything you could possibly be asked about a graph. Like I said, sometimes I will break a question like this into 3 different problems. First part, I ask you about increasing, decreasing, relative max and min. Second part about concavity and inflection points. And third part, putting everything together, getting the actual graph.